I want you to imagine something for a second. Just picture opening up your kitchen pantry. You reach past the salt, the pepper, the olive oil, and you grab a little shaker of MSG. You know, that famous umami seasoning you might sprinkle on some fried rice.
Oh, yeah, the magic flavor dust.
Exactly, the magic dust. Now, I want you to imagine taking that exact same shaker of food seasoning and somehow using it to power the world's most advanced artificial intelligence supercomputer.
Which, I mean, sounds like a glitch in the Matrix, right?
Yeah.
Or just a really weird cooking show.
It really does sound completely made up. But welcome to the Deep Dive Lab. Today, we actually have a super bizarre mystery to solve for you.
Yeah, it's a really fun one today.
It is. So our mission is to take this massive stack of material science research papers, some industry market reports, and these really obscure innovation archives, and basically figure out how those two completely different worlds collided.
Right, the food world and the tech world.
Exactly. The central question we are exploring today is this. Why does a Japanese food company, Ajinomoto, the company literally famous for creating the umami flavor, why do they hold a near 100% monopoly on a microscopic component inside, like almost every single high-performance computer, smartphone, and AI data center on Earth?
It is genuinely, without a doubt, one of the most fascinating supply chain anomalies in modern history. I mean, you have this massive multi-trillion-dollar tech industry entirely relying on a foundational technology that was born from food chemistry.
It's wild. It's like finding out your favorite hot dog vendor secretly burns the engines for NASA rockets or something.
That is exactly what it feels like.
But, you know, to figure out how we actually got here, we can't start with modern AI. We have to go back to a time when the computer industry was absolutely panicking.
Yeah, full-blown panic mode.
We're talking the 1990s, so set the scene for us. What was happening?
Okay, so think back to the mid-90s. The world was undergoing this massive, pretty painful transition from MS-DOS to the Windows operating system.
Oh, man, yeah. Going from typing the green text on a black screen to actually having a mouse and clicking on colorful icons.
Exactly that shift, that leap to a graphical user interface, or a GUI, it changed absolutely everything under the hood. Suddenly, CPUs weren't just processing basic text commands anymore. They were handling massive, massive amounts of graphical data.
Right. The workload just skyrocketed.
Skyrocketed. And because of this, the actual physical architecture of the microchip had to change drastically just to keep up. So almost overnight, the number of connection terminals on a single chip exploded. It went from about 40 pins to over 1,000.
1,000 microscopic wires coming out of one tiny chip. I mean, just picturing that makes my head spin. How do you even organize that without them all just crossing and tangling?
Oh, that was the billion-dollar question at the time. All of these tiny, incredibly dense copper wires needed to be perfectly, and I mean perfectly electrically insulated from one another.
If they touch, it's game over, right?
Right. If they aren't completely shielded, the electricity just jumps between the wires. You get a catastrophic short circuit, and your brand new, incredibly expensive processor is instantly fried. It's garbage.
So what was the industry doing before they hit this sudden, 1,000 pin wall?
The standard at the time was using liquid ink insulators. You would literally coat the circuit board in a special liquid polymer to shield the wiring.
Okay, wait. Applying a liquid ink actually sounds pretty straightforward. I mean, you just spread it out like painting a wall. Why was that suddenly causing such a massive panic for these new complex chips?
So painting a wall is a great way to picture it, but let's stretch that analogy a bit. Imagine if the paint on that wall had to be perfectly uniform down to the absolute microscopic level.
Okay, tough to do with a roller.
Very tough. And if you left a single microscopic air bubble in that paint, your entire house burns down.
Oh, wow.
Yeah, that was the reality of using liquid ink on these new, dense processors.
So the margin for error was just zero.
Below zero, honestly. And the actual application process was an absolute nightmare for mass production. It required this painstaking multi-step routine.
What? What did they have to do?
Well, you had to coat the substrate in a clean room, wait for it to dry, then physically flip the entire delicate board over, coat the other side, and wait for it to dry again.
That sounds incredibly slow, especially for an industry trying to put a computer in every single home.
It was a huge bottleneck.
But, if it was just a speed issue, why couldn't the massive Silicon Valley giants, like the DuPonts and 3Ms of the world, just invent a better liquid? Or a faster drying process?
I mean, they certainly tried. They threw a lot of money at it. But they were hitting a fundamental wall of physics and chemistry. As the liquid dried, It was just naturally highly prone to trapping microscopic air bubbles.
Because it's a liquid, it moves around.
Exactly. It naturally applied unevenly at the edges of the board. And to top it all off, the drying process released harmful, toxic gases.
Oh, great. So it's toxic too.
Yeah. The tech companies were completely stumped. They desperately needed a solid, reliable, microscopic way to insulate the wiring, and they just couldn't figure out a scalable alternative to the liquid mess.
And this is where the story takes a massive left turn. Because the solution didn't come from a high-tech Silicon Valley lab, it came from a food company.
It really is wild.
Tell me about Ajinomoto, because this transition is just fascinating.
So to understand Ajinomoto, we actually have to step even further back to the 1970s. Ajinomoto is an absolute titan in the food industry. They basically discovered and commercialized the umami flavor.
Right, the MSG guys.
The MSG guys.
Yeah.
And to mass produce MSG on a global scale, they developed a very deep, sophisticated understanding of organic chemistry.
Which makes total sense. I mean, flavor is just chemistry at the end of the day.
Right, exactly. They were heavily invested in what they branded as aminoscience, applying their deep knowledge of amino acid chemistry to entirely new fields outside of food.
Okay, so they're experimenting.
Yes. Now, during the production of MSG, they ended up with a chemical byproduct called chlorinated paraffin.
Chlorinated paraffin. I'm going to go out on a limb and guess that does not go on a salad.
Definitely not. No, it's an industrial byproduct. But their researchers, basically acting out of pure scientific curiosity, started testing this byproduct to see if it had any useful properties.
Just tinkering in the lab.
Just tinkering. And they discovered that this chlorinated paraffin had a really unique, powerful softening effect on certain resins.
Okay, chemistry is not my strongest subject, so I might need a little help connecting the dots here. How do we get from softening resins in the 70s to fixing computer chips in the 90s?
So fast forward a couple of decades. The computer industry is screaming for a better insulator, right? Ajinomoto researchers hear about this, and they start applying their aminoscience expertise to epoxy resins.
Oh, I see.
Yeah. By combining an organic epoxy resin, a specialized hardener, and inorganic silica microparticles, they eventually engineered something totally revolutionary. They created a thermosetting film.
A film. Okay, so not a liquid at all.
Exactly. A completely solid, dry film. Think of it almost like a microscopic layer of incredibly advanced plastic wrap.
Wow.
And the beauty of it was that it could be laminated onto a circuit board in one clean single layer using just heat and pressure.
Because it wasn't a liquid, there were absolutely no air bubbles.
None.
Well,
There was no uneven drying. And there were no toxic fumes. It solved literally every problem the liquid had. It was named Ajinomoto buildup film, or ABF.
so they basically just ironed it on like a patch on a denim jacket that solves the liquid mess entirely. But, reading through these engineering reports for this deep dive, the real magic here isn't just that it's a solid film. It's what having a solid film allowed chip makers to actually do.
Yes, exactly.
I really want to dig into something called SAP, or the semi-additive process, because this seems to be the exact moment the tech industry changed forever.
It was a total paradigm shift in how we manufacture electronics.
Yeah.
Before ABF existed, circuit boards were made subtractively.
Subtractive, meaning you start with a lot of material and take it away. Like carving a statue out of a massive block of marble, you just chip away everything that isn't the statue.
That's a really good way to visualize it. In the old process, you would start with a thick layer of copper foil. Then you would use harsh chemicals to literally etch away all the copper you didn't want, leaving behind the remaining copper to act as your electrical wires.
But the problem with carving copper with acid is that the acid doesn't just eat straight down, right? Like if I'm carving my marble statue with acid, the acid might melt the nose while I'm just trying to carve the cheek.
That is a very vivid but very accurate way to put it. Because of that undercut from the acid, you end up with wires that have jagged trapezoidal shapes instead of perfect squares.
Right, they're wide at the bottom.
Exactly. And because they are jagged and wide at the base, there is a hard physical limit to how close you can pack those wires together. With subtractive etching, the minimum width you could achieve was stuck at around 40 micrometers.
You couldn't get any smaller without the wires bleeding into each other and short-circuiting.
Precisely. You hit a wall.
Which is a huge problem, because if you can't make the wires smaller, you can't make the chips more powerful, you essentially halt Moore's law entirely. So how does SAP, this semi-additive process, how does that flip the script?
With SAP, you throw the marble block away entirely.
Oh, okay.
Instead of starting with a thick block of copper and carving it away, You start with a completely bare, perfectly smooth layer of Ajinomoto buildup film. Then you lay down a microscopic seed layer of copper on top of the film. We're talking incredibly thin, maybe zero point 0.1 micrometers.
Okay, so instead of carving a statue, SAP is more like 3D printing only the exact structure you need from scratch directly onto the film.
Yes, exactly. You use a light-sensitive mask to define specifically where the wires should go. Then you electroplate copper only into those tiny defined channels.
So you're building it up, not tearing it down.
Right. And when you're done building the wire up, you just do a very quick flash etch to remove that tiny seed layer. The end result, perfectly straight sidewalls.
Wow.
No jagged trapezoids, no wasted space.
And because the sidewalls are perfectly straight, you can pack them incredibly close together.
The leap in density was astronomical. Using ABF and the semi-additive process, manufacturers could suddenly shrink wiring down from 40 micrometers to 5 micrometers.
Well, a massive jump.
And today they're pushing down to 2 micrometers.
Let's zoom in on those micro-level details for a second, because the sheer scale here is just hard for the human brain to wrap around. A single layer of this ABF film is applied about 10 to 15 micrometers thick.
Super thin.
Yeah. For context, a standard human hair is about 80 micrometers thick, so this film is a tiny fraction of the width of a single hair.
And the structures built into it get even smaller. Once the film is laid down, they use UV lasers to drill tiny holes called microvias into the film, which allow them to connect the different layers of circuitry vertically.
Right, like an elevator shaft between the floors of the chip.
Exactly. And those laser-drilled holes are as small as 3 to 10 micrometers across.
Okay, I want to pause here because I was reading through some of the engineering literature for high-speed transmission to prep for this, and I found a specific study by a researcher named Shiro Tatsumi and his colleagues from Ajinomoto.
Oh yes, Tatsumi's work is foundational.
Yeah, they were detailing the creation of their advanced GX and GZ series of ABF. And I'll be honest, a lot of the chemistry went right over my head. But what stood out was how they engineered the epoxy with those inorganic silica microparticles to drastically lower something called the dissipation factor, or D.
Ah, yes. The dissipation factor. This is where the chemistry of the film directly dictates the physics of modern computing.
I really need you to break this down for me. I'm looking at charts of decimal points and chemical bonds, but why does the dissipation factor actually matter to you listening to this deep dive right now? Like, why should anyone care about the DF of a piece of invisible plastic?
To put it bluntly, it determines whether the modern internet actually works.
That's a big claim.
It is, but it's true. Before we talk about ABF's dissipation factor, let's look at what came before it. If you've ever cracked open an old electronic device, like a broken TV remote, you've probably seen a stiff, dark green circuit board.
Oh yeah, totally. The classic green board, everyone knows that look.
Right. That classic green material is usually something called FR4 fiberglass. It's an incredibly common, cheap insulator. And for an old TV remote, it works perfectly fine. But FR4 has a relatively high dissipation factor around 0.015.
Okay, and what does that number actually mean in practice, like mechanically?
It means it absorbs energy. When you are transmitting data at incredibly high frequencies, like the 25 plus gigabits per second speeds required for modern internet routing, 5G networks, and artificial intelligence, the electrical signals start to behave differently. Well, as they travel through a material at high speed, some of that electromagnetic energy leaks out. It's absorbed by the insulating material and literally turned into heat. That loss of signal energy is the dissipation factor.
Got it. So a high DF, like in that old green fiberglass, means your signal gets eaten up by the board itself before it can even reach its destination?
Precisely. At modern high frequencies, FR4 is incredibly lossy. The signal degrades rapidly. But Tatsumi's research showed that by engineering the ABF with highly specialized resins and silica fillers, specifically their advanced GL series, they could push that D down below 0.005.
Which is a massive drop. So to put that in perspective for the listener, this is the literal difference between a high-speed signal arriving perfectly intact to scream a 4K movie or arriving at the other end of the chip as completely scrambled garbage.
Without that phenomenally low DF, you simply do not get 5G telecommunications. You don't get high-speed video streaming. You don't get cloud computing. It is foundational to how data moves today.
But hold on. That raises a huge red flag for me. You just mentioned that the lost signal energy turns into heat. And we all know computers run hot. I mean, my laptop gets hot enough to burn my legs if I have too many browser tabs open.
Oh, we've all been there.
Right. So how on earth does a plastic film that is a fraction of the thickness of a human hair not just instantly melt or warp or snap in half when the processor heats up to those extreme temperatures?
That is the ultimate mechanical challenge of semiconductor packaging. It's one thing to be electrically sound. It's another thing entirely to survive the physical torture chamber of a hot
Oh,
CPU.
torture chamber, yeah.
And this brings us to another really fascinating piece of research. There was a study published in the scientific journal MDPI that numerically investigated crack suppression in advanced substrates. And the key metric they were analyzing was ABF's coefficient of thermal expansion, or CTE.
Coefficient of thermal expansion, let me try to break that down. Basically, this measures how much a material swells up when it gets hot and how much it shrinks when it gets cold, right?
Exactly.
Like how a suspension bridge has those interlocking metal expansion joints so the concrete doesn't buckle and crack in the summer heat.
That's a perfect analogy. Now, apply that to the microscopic world inside a microchip. You have a silicon die, which is the brain of the chip,
Yeah.
and you have copper wiring. Silicon and copper have entirely different rates of expansion.
Oh, okay, so they grow at different speeds.
Right. If you glue them together with a plastic insulator that expands at a totally wildly different rate when it gets hot, the entire package will warp.
Because one material is stretching out faster than the others, it would literally tear itself apart from the inside out every single time you booted up a heavy software program.
The mechanical stress would be immense. It would shear the microscopic solder joints right off the board. But the MDPI study highlighted something incredible about how Ajinomoto designed ABF.
What did they do?
Those silica fillers packed inside the epoxy, they act as a physical anchor. By carefully tuning the ratio of the organic epoxy matrix to the inorganic silica particles, Ajinomoto engineered the film to have a CTE of around 20 to 55 parts per million per degree Celsius.
Okay, meaning it expands and contracts at a rate that is incredibly similar to the copper and the silicon it's attached to.
Yes, it acts as a mechanical buffer. It brings harmony to the whole structure. It's not just an electrical insulator. It provides vital structural integrity. It keeps the chip physically intact while handling these massive, violent thermal cycles.
That is genius. Which, brings us to the biggest trend in the world right now. The absolute explosion of artificial intelligence over the last few years.
Oh, absolutely.
If we connect all this chemistry back to the bigger picture, the AI revolution is fundamentally a hardware revolution, isn't it?
Without a doubt. We tend to think of AI as software, as chatbots and image generators. But training those large language models requires an unimaginable amount of physical computational horsepower.
And reading through the market data, the sheer scale of ABF used in these modern AI chips is staggering. Just to give you a sense of scale, a standard PC processor, the kind you might use at home to check emails and watch YouTube, might use 6 layers of ABF to route its internal wiring.
Which is already a lot of dense engineering.
Right. But if you look at modern AI GPUs, the massive, expensive chips driving the latest AI models, they require 18 to 20 plus layers of ABF.
The complexity is scaling vertically now. Modern chip makers are stacking multiple chiplets together to act as one giant superbrain. The wiring required to connect all those distinct brains together flawlessly is incredibly dense, and it relies entirely on those multiple layers of ABF to insulate the connections.
The industry reports estimate that a single high-end AI GPU consumes 15 to 20 times more ABF material than a standard laptop processor. 15 to 20 times the material per chip.
And this is where the market dynamics become almost unbelievable. Because of how perfectly tuned ABF is, its incredibly low dissipation factor, its precise coefficient of thermal expansion, its ability to support 2-micrometer wiring without bubbling it, has become the absolute de facto standard.
And no one else can touch them.
Not really, no. Ajinomoto Fine Techno controls an estimated 80% to over 95% of the global market for these high-performance insulating films.
95%. That is a true, undeniable global monopoly. It's just wild to think about. We talk so much about the software of AI or the massive silicon foundries building the chips, but there is a literal physical bottleneck sitting in a chemical plant making a 10-micrometer film, without which none of this futuristic technology works.
And you better believe the broader tech industry is actively trying to find alternatives, purely to mitigate the risk of relying on a single supply chain. I mean, there are massive chemical companies trying to qualify other thermosetting films. But displacing an incumbent like Ajinomoto is incredibly difficult.
Why is it so hard, though? If you have billions of dollars, can't you just reverse engineer the chemistry and make your own film?
Well, it's not just about the recipe. It's about the manufacturing trust.
Trust.
Yeah. Ajinomoto has 25 years of deep, proprietary integration into the chip manufacturing process. Major foundries build their entire multi-billion-dollar assembly lines around the exact thermal and chemical properties of ABF.
Oh, I see.
If you swap out the film, it causes even a 1% increase in failure rates on a GPU that costs tens of thousands of dollars. It's a financial disaster.
Yeah.
The industry is highly, highly risk-averse when it comes to changing the foundational recipe.
Wow. So they are effectively locked in by their own massive success.
Let's step back and recap this incredible narrative journey, because we started looking in the kitchen pantry and we ended up at the bleeding edge of global infrastructure.
It's quite the trip. In the 1970s, scientists at a food company were just trying to figure out what to do with a byproduct of making umami seasoning. And through decades of pure scientific curiosity and aminoscience, that byproduct helped lead to the creation of a miraculous 10-micrometer thermosetting film.
Which is just so cool.
And that film solved a massive manufacturing crisis in the 1990s, allowing microscopic wires to shrink from 40 micrometers down to 2 micrometers using the semi-additive process. And today, that exact same lineage of film is the foundational bedrock of the 21st century digital economy and the artificial intelligence revolution.
It really is a brilliant example of how cross-pollination in science creates the biggest breakthroughs. The answers don't always come from the experts in your own field. And importantly, the technology isn't standing still.
Oh, definitely not.
Researchers are already looking at what's next because, as you noted, stacking 20 layers of film on an AI chip means we are rapidly approaching another physical limit.
So what does the future look like? Where do we actually go from here?
The next major frontier is integrating ABF with entirely new architectures, specifically glass core substrates.
Glass, like actual glass.
Yeah, actual glass. It's incredibly flat and handles high-frequency signals and heat exceptionally well, but it's very brittle. So researchers are now looking at using next-generation ABF as an advanced adhesive and redistribution layer on top of the glass.
Oh, that's clever. Marrying the two materials to get the best of both worlds.
Exactly. Combining the extreme flatness of glass with the microscopic wiring capabilities of ABF. Furthermore, from a sustainability standpoint, the data center boom is putting a massive strain on the environment.
Yeah, the power draw is insane.
Right. So Ajinomoto is currently exploring what they call green ABF. They're returning to their roots in organic chemistry to develop palm oil-free, bio-based materials for the film.
Wow.
The goal is to make the underlying physical hardware of these massive AI data centers more environmentally sustainable, without sacrificing that crucial electrical performance.
That is just amazing to me, from food seasoning to computer processors and now returning to organic biology to make the processors greener. It leaves you with a really lingering, provocative thought.
Yeah, it really does.
If the critical bottleneck of modern supercomputing, the absolute ceiling of human technological advancement in the 90s, was unexpectedly solved by scientists studying food flavorings, what other massive technological leaps are currently hiding in entirely unrelated industries?
Just sitting there.
Just sitting there, waiting for someone curious enough to connect the dots.
It really makes you wonder what the next ABF will be and what strange, unrelated industry it will come from.
It absolutely does. I'm going to look at my takeout completely differently tonight, that's for sure. Well, thank you for joining us in the Deep Dive Lab. If you loved uncovering the scientific mystery, and if you agree that science is so much stranger and more fascinating than fiction, be sure to follow and subscribe for more unexpected stories from the bleeding edge of discovery. See you next time.